So good morning. We continue with our discussion on the linear systems with constant coefficients, and we take up the special cases which is reasonably simple in the sense that we assume the operator represented by the n by n matrix A is diagonalizable. So this is the problem that we have. Ax with A is taken as Aij. Assume this is the scenario that we are taking up. It's a homogeneous first order linear system consisting of n simultaneous equations. Now this is of the form, in fact, dxi by dt equal to sigma j equal to 1 to n aij. These are constants. Xj we are going to take advantage of the fact that the coefficients are constants. That's why we are able to explicitly solve the problem. Otherwise, in general, it is extremely difficult to handle even the linear case, not to talk about the nonlinear problems. And as I was telling, very often the theory of differential equation is a consequence of this inability to explicitly solve many of the equations, or most of the equations, I would say. There are very handful of equations which can be solved explicitly. Okay, so this is a case where we can exploit our knowledge of linear algebra considerably and even reduce, I would say, even reduce this analytical problem to an algebraic problem. And we have already had a good background of linear algebra, so we shall see how it comes into play in a very, very positive way in this case. Now, before that, we make certain observations. So, first of all, the existence and uniqueness theorem applies here. Therefore, given an initial data, you are assured of a unique solution for this problem, and in fact every solution is defined on the entire t interval, namely from minus infinity to plus infinity. All solutions are defined for every t belonging to . This is something which comes out from all the efforts that we have taken to develop, to have a look at the theory. Now, we make some observations. The first observation that we make is that the make a simple observation which is very handy many places. Observe, or if you want you can put it as a lemma. If xt is a solution, so this we call system 1. Solution of 1 x prime t, that is x derivative of t, is also a solution of 1. It's quite easy to prove. So given, proof, x. Now you just differentiate it. You just differentiate. So x is a solution of this equation. Therefore, differentiating, d by dt of now A is a constant matrix, therefore this is equal to, therefore if you set this is equal to Ax prime. So it's clear that x prime is a solution of this is a general result that will be that is true for the constant coefficient case, which is very handy in our in developing some part of the solution. So now we want to make a remark. If I write d dt and PD equal to I or simply P naught, then PD x t is a solution 1 whenever x is this means that for any polynomial p with real coefficients, let us say, not complicated at the moment, with the real coefficients p1, p2, etc., pn, where of course pi's one can as well write it for complex constant. I mean, there is no problem. But let us, for the time being, take this. Then PD of x is also a solution whenever xt is a solution of R. Now, this is one simple observation and a consequence of the lemma that we have proved. Now, a second scenario that we encounter while working on this is this. We may come across complex solutions. Now, a simple example for this is this. Suppose A is given by zero, then e to the power times that is quite easy to check. This is something which you can easily verify. Therefore, so we make one observation. We are keeping Aij to be real, and whatever I state now is valid only when you take Aij to be real. If oh, sorry, I think I should put here only zero or something. Okay. solution of one, then real part of and imaginary part of this is quite easy. So what do you mean by real xt and imaginary xt? See, xt is taken as they are all now assumed to be complex valued functions. Therefore, and we write real xt and so also imaginary part of xt these are notations basically. Then we can show that this is a solution. I mean, this is quite easy to verify. So xt can be written as real I times where I is equal to square root of minus 1. Then you see that axt equal to a is real, therefore it is real part of because a is real. Now you can see that we have dx by dt is also equal to d by dt of and dx by dt equal to axt implies, I mean, equating the real and imaginary parts on either side, you get because you have a real part of a xt is the same as a of real part of xt plus I times a of Sorry, I think I'll just remove this. And here we have used that and imaginary part of this we have used, and that is possible because A is a real n by n matrix. So this is true. Therefore, what we have? So the real and imaginary a complex solution are real solutions of one. That is what we infer. Okay, now this is a very useful information, but this works, let me just emphasize, this works only when A is a real n by n matrix. So we don't otherwise make this statement, otherwise the statement is not true. Now what do we have now? Suppose you have a, you know that dimension of it's an n-dimensional vector space. Now what we can show is that, see, once you get complex solutions, from that you can construct real solutions. Okay, if you have complex solutions, so certainly you get real solutions constructed, more number of real solutions constructed. Now you see that if you have a fundamental set of solutions, real or complex, determined, then their real and imaginary parts also give you a new set of solutions, and this may be more than n, but you cannot have more than n linearly independent solutions. Therefore, what you can have is that from this collection, so in general, from the collection of solutions where xjt solutions of 1 which may not be real. Xj's need not be real. Okay, as you have seen that in some cases you come across that, as we are going to see soon later. Okay, we can construct a basis for the solution space of 1 solution a basis consisting of real solutions. Consisting of in real solutions. Now this is one of the advantages that we have. We will return to this point later. Okay, so for the time being we'll just keep it in our mind that you can construct a fundamental set of solutions which are real solutions. Okay, so from a complex set of n linearly independent complex solutions, you can always construct a set of n linearly independent real solutions. All this happens assuming this A is real, otherwise it may not work. In fact, it doesn't work. Otherwise you cannot write these things like real and imaginary parts are solutions, etc. cannot be stated otherwise. Okay, so let us now make some assumptions. So our assumptions, this is the initial one, but later we will generalize this. A is diagonalizable as an element of R with real eigenvalues. This is the first assumption that we make. And in this case, let us explore the scenario. Right. So what are the assumptions that we make? One, A is diagonalizable. And from linear algebra, we know we find the eigenvalues and eigenvectors and use that to diagonalize the operator. with the diagonal elements given by the eigenvalues. We don't even, let us not even assume that all eigenvalues are distinct. That is not really needed. But it is diagonalizable. If it is not diagonalizable, then it's more complicated, and we will explore that, or how it can be explored, we will investigate later. But for the time being, we will work with this. Yeah. So let us make this assumption. You see, this class of diagonalizable operators with real eigenvalues is not a small class. It's a reasonably big class, because you know that this class is not a small collection. In fact, if A is symmetric, that means A satisfies this property. In this case, you can prove that all the eigenvalues are real, and A is diagonalizable. I mean, A is diagonalizable means something more. That means, see, recall if the eigenspaces take Rn over R as a vector space, and there this is the case. That means you can find n eigenvectors of A which will form a basis for Rn. Okay. So let us write it more explicitly. Let be the k distinct eigenvalues, real eigenvalues, because we are assuming all of them are real, each with with multiplicities n1 that is, we are talking about the algebraic multiplicity. Assume dimension of the null space of A minus lambda j I is equal to nj for j equal to then that means you see that the eigenvectors belonging to distinct eigenvalues are linearly independent. So what do you have? Hence there exists an ordered basis for Rn with eigenvectors of it. This is what we have proved in the case of linear algebra. That means, see, you can have n eigenvectors of A belonging to the eigenvalue lambda j, sorry, nj lambda j. Okay. Right. So what you have is this: Rn is the direct sum of null space of A minus I and dimension of dj where of course distinct eigenvalues. No, not that. Okay. This is what you have, and if belonging to lambda j, its span spanning the null space of A minus lambda 3. The set of n vectors for and they are all and xij or xj r is a eigenvalue of, so this is the sum total of what we know from about diagonalizable operators. Okay. We'll take the complex case is not coming up because in this case you will see that they are already real vectors. They are all automatically real vectors. So in the complex case we need some more details to work with. We shall take it up later. Okay, so let us work on this. Now we prove the following theorem. So what we have is, if we take the initial data as an eigenvector for the problem dx by dt equal to ax, with x t naught or x0 equal to some x naught, suppose it is an eigenvector, then the corresponding solution xt also turns out to be an eigenvector for each choice of t. Now this is something very interesting. I don't know whether you catch what I said. Let solution of 1 such that for some value of t, equal to t naught, xt naught, you see xt naught is now a vector in Rn, is an eigenvector of A belonging to the eigenvalue lambda. Okay, then what we have is, or rather we can write this, that is A x t naught equal to lambda t naught. It's a non-zero solution. Then what we can infer is that for every t, A is identically equal to, this is a big breakthrough. Okay, so this is a, and such vectors are called the characteristic solution of 1. So we will prove this first and then make some remarks. Define yt as minus xt for every t, belonging to minus infinity to plus infinity. Then because yt is equal to dx by dt is, okay, okay, because what you have is this, equal to dx by dt is xt. Now if we can prove that yt is identically equal to 0, then we get dx by dt equal to lambda xt, or what you call axt. A is the or xt is the eigenvector of A for every t. Okay. Now we observe that, look at this problem. So this is a solution of 1. That is because if x is a solution of 1, then x derivative is also a solution of 1, and so you have this result. And therefore dx by dt is equal to axt minus this. Therefore yt is one such that yt not equal to 0. Why yt not equal to 0? Because yt naught is equal to dx by dt at t naught minus lambda ax t naught minus lambda x t naught. This comes from here. Okay. Therefore, what you get? See, this is true. To the eigenvalue therefore yt naught is equal to 0. So yt is a solution of 1 such that yt naught is the 0 vector. Hence for every t. And what does that mean? That means A or xt is now this is something that we are going to make use of. Okay. Therefore, what do we infer? So we want to find out eigenvector of A for, or it is enough to find out a vector which is an eigenvector of A and set xt naught equal to that vector, then you get the solution. Okay. So this we have proved. Okay. I will make a remark. You see, there is a terminology that an eigenvector is also a characteristic vector, an eigenvalue is also called a characteristic value. Okay. So we shall call this as a characteristic solution of belonging to the eigenvalue lambda. So this is the terminology that we use. So we are essentially, if we are interested to get a general solution, then all that we need is to develop a fundamental set of solutions. And how do we do that? Now the path is clear, because what one does is take A, find a basis consisting of eigenvectors of A for Rn. Corresponding to each such vector, you construct a solution. And then this solution set also has this property. Because of this theorem, it follows that dx by dt, or A is a eigenvector of xt is an eigenvector of A corresponding to lambda for every t. We'll use this. So how do we proceed? We are looking forward to construct a solution, a general solution of So what do we do? Let us choose an ordered basis for Rn with eigenvectors of that is possible, because we assumed that this is possible since A is diagonalizable. A is diagonalizable. Let be these vectors. These are eigenvectors of A. Okay. Now you solve this problem. Dx by dt equal to Ax, subject to the condition that x at t naught equal to xj r. Okay, so 1 r is in fact 1 less than or equal to r aj. So there are n such solutions that you can find. Then what one gets is that this 1 less than or equal to j with n1 equal to n. Form a fundamental set of solutions of 1. This is the outcome that you have. Now let us see the structure of this solution. What is the structure of this solution? So let eigenvalue of A with an eigenvector x which is equal to Rn belonging to, okay. Now what you have is this. See, you have dx by dt so if xt is denoted by x and t, then what we have is this dx by dt ax That means, but Ax equal to therefore what you have, dx by dt this is equal to xi. So they separate. See, this set of simultaneous equations separate once we take the eigenfunctions. Okay, this is true for I equal to where Ci is an arbitrary constant and xi t naught is now equal to Ci e to the power lambda t naught. Therefore, but xi t naught x naught is equal to xi. Okay, then Ci we can evaluate. This is equal to xi into e to the power lambda this is for I equal to, if we take for I equal to, therefore what is the solution? The solution that you get, the corresponding solution is given by just the standard vector or the eigenvector that you have chosen multiplied by e to the power lambda. Okay, so that's the result, that is xt equal to so the problem reduces to determining the eigenvalues lambda and the corresponding eigenvectors. the eigenvalues of lambda corresponding eigenvectors. Each of the eigenvectors. Once you determine that, you can immediately get the solution written in this form. Quite simple. So lambdas, you put the corresponding eigenvalues, and with the associated or the eigenvector belonging to the eigenvalues will give you the result. Okay, now let me just work this out. So let us also prove one more result. Any set of characteristic solutions of the equation 1 distinct belonging to different characteristic values or eigenvalues A linearly independent. That is quite easy to prove. Straight away one can prove that. In particular, A has n different characteristic solutions which forms a fundamental system of solutions so that every general solution is a linear combination of these fundamental set of solutions. Okay. So this is quite easy to prove, because I don't want to write a proof of this, because you see that any set of characteristic solutions of one belonging to different eigen characteristic values of A is linearly independent. That's a simple thing, because you see that if you are talking about characteristic solutions of one, then at any point t naught, they form what is called a characteristic vector belonging to the particular eigen value, and they belong to different characteristic values. So you know that the vectors, eigen vectors belonging to distinct characteristic values are linearly independent. Okay. Therefore, it follows that the functions x1, x2, etc., xk, they are also linearly independent if they belong to distinct characteristic values. And in fact, what we have is that we have broken up the space Rn into the what you call the null spaces of A minus lambda I. Okay. Right, on each of which is an eigenspace belonging to a particular eigenvalue, and we are assuming that A is diagonalizable. Therefore, you see that the algebraic dimension of A is the same as the geometric dimension of for a particular eigenvalue. Okay, so that advantage we have, we are going to make use of that. Okay, so I will just go to some problems where you can work out this. So let me take the following equations. First, take an example where you have real eigenvalues, but all of them are distinct. So, take dx by dt equal to 1, 2, 1, 2, 1, 2, 1, 1. Suppose this is the equation that you have to solve and find a fundamental set of solutions. So, as I said, this analytical problem is now reduced to an algebraic problem. So, we have A equal to 1, 1, 2, 1, 2, 1, 2, 1, 1 belonging to R3. Okay, find the eigenvalues. So, what is the characteristic polynomial? Of A is given by determinant of, which is, in this case you can work it out. If you work this out, this will turn out to be minus Okay. Therefore, are the three distinct eigenvalues of So what do? We now determine the eigenvectors. So one can easily solve this equation. So what do you do? So for instance, you solve. So solve equal to 0 for I equal to 1, 2, 3 to determine eigenvectors A belonging to eigenvalue lambda I. So if you do that, this is what you end up with. That is called lambda 1 then the eigenspaces are null spaces of I. Or you can show this. I mean, that is so A minus lambda 1 is what? Lambda 1 equal to 1. A minus I span of, this is the eigenvector belonging to that. I have it computed here. One. Null space of A minus A plus I span of the vector So these are the three vectors that you have. Okay, this is your x1, x2 and x3. Therefore, what is the solution? Therefore, A is given by the following. What is it? e to the power t, you have 1 0 minus 1 e to the power minus t and 1 1 1. This gives the fundamental set of solutions of 1. Okay, that is a general solution of is C1 into 1 minus 2 1 plus C2 into 1 0 minus 1 where arbitrary so that gives the general solution. Okay, so the problem is very simple. Once you get the eigenvalues and eigenvectors, and if you know that the eigenvectors span the whole space, then you have a fundamental set of solutions. Okay, that's what we have assumed, that we are now taking up the case where the eigenvectors, you can find set of n eigenvectors which span the whole space. Now let us take a problem where you have multiple eigenvalues. This is all eigenvalues are distinct. Now we take up the next problem. This is a very simple problem. Take dx by dt dx where a is given by 0 1 1 1 0 1 1 0. Now here the characteristic polynomial a is then minus lambda cube plus 3 lambda equal to 0, that is minus so you have a multiple eigenvalue. The multiplicity of 2 has multiplicity 1 and minus 1 has multiplicity 2. So we take lambda 1 equal to 2, lambda 2 equal to minus 1, lambda 3 also equal to minus 1. Okay. Now you see that 1 1 1 is an eigenvector of A belonging to now you see that you can see that the dimension of A plus I is equal to 2, that you can easily settle, and we can choose a basis for that, 1 0 minus 1, and this is the same equation, 1 0 minus 1, and forms linearly independent vectors spanning right. Therefore, what do? You get the corresponding solution for the problem. Equation 1 has solution given by a fundamental set of solutions given by, we have what are the vectors that you have? Yeah, 1 1 1 into e to the power 2t and then you have minus 1 1 0 minus 1 into e to the power minus t, then again one more 0 1 minus 1 to e to the power minus t. Therefore, a general solution is C1 into 1 1 1 e to the power 20 plus C2 into e to the power minus t plus C3 into in this context, you should also remember that if a vector x is an eigenvector of A belonging to the eigenvalue lambda, then any scalar multiple of that is also an eigenvector whenever that scalar is not equal to 0. Okay, so that goes without saying. Okay, so these are the two examples that I have given where the eigenvalues are all different. When the eigenvalues are all different, then naturally you have three eigenvalues in this case. In the general scenario, there are n distinct eigenvalues, and then there are n distinct eigenvectors that you can get, which are linearly independent and form a fundamental set of solutions for, or a fundamental set of vectors for Rn. And correspondingly, you can immediately write down the solutions. Okay, so this gives sort of example. Now what you do is the C1, C2, C3 are arbitrary. Now what you do is, suppose you are given an initial condition xt naught is equal to some x naught. In that case, you have to determine C1, C2, C3 such that xt naught is equal to x naught, and you can see that these vectors are linearly independent. Therefore, you can easily see that one can solve the corresponding equations for determining C1, C2, C3 uniquely. That means you have a particular solution satisfying the required condition. So this is the general solution. Once you get the general solution, from that you can always get the specific solution satisfying a given initial data. So I think you can take up different problems, and maybe I can write down a couple of problems or 2-3 problems where you can have a go and get a feel for that. So exercises, I just write exercises and then leave you with that. It needs some kind of a careful working to find out the eigenvalues and eigenvectors. And these eigenvectors are not unique. That, of course, you should know. So I'll give some examples where you can work this out. Where A is given by this. Some 1, 2, 3 solution. So you find the general solution and then find the particular solution. Second problem is this. No, sorry, I think the first one has problems. I have wrongly printed the problem. So you take this problem. The second problem you take. The other problem has difficulties that we will take up later. In this case, you can see that it can be solved using this method. The second problem is, you can take up these problems. In both these cases, find the general solution. Okay, so that completes the proof of this. That completes this particular lecture. Now what we take up is the following. Make a more complicated. It's not, we take up two different cases. One, we end up getting what are called complex solutions. And in that case, how do you get a fundamental system of solutions? That is the first one. The second one is where you see that you run into difficulties to getting a basis for the vector space Rn consisting of only the eigenvalues, only the eigenvectors. Okay, that means we go to the more general situation where the operator A is not diagonalizable. In that case, how do you approach the problem? Now this is the more sophisticated case that we have to consider, but otherwise this is a simple case that we have looked at. Okay. So here we have also considered the cases where you get eigenvalues of multiplicity more than one. But we have assumed that all the eigenvalues are real. A complex case we will take it up. Okay. So thank you very much.